So I want to thank everyone coming to this week's SMLI workshop. I'd like to also welcome our speaker, Neev. He will be giving his talk on graph networks and an application to deep reinforcement learning. I'll be honest, I'm very excited about this. This is our first talk about graph networks. And I think, they're very interesting, more modern and current technique that's being used in machine learning. And I'm really excited to be able to learn more about this. So Neev, if you want, you can take it away.
All right, thank you, everyone. Thank you, Bjorn. Hi, everyone. Thank you for coming. I am Neev. I'm an undergraduate junior at Brown CS, and I've been, conducting research with Professor Kanadaris for almost a year now. And I'm here to sort of give you guys a little primer on neural networks and how we've seen applications in various places, and more specifically, where we've seen this in deep RL, because that's where my research is. So yeah, let's get started. An overview of sort of why we want to do this, right? So the whole point is people saw a need to, take this powerful technique of deep learning and the success that it's seen, with ImageNet and a bunch of other things, like with NLP, with BERT and so on and so forth. They've wanted to take these techniques and apply them to graphs. And why is that? That's because graphs are a natural way to express like rich, complex information. Because what you can do is you have a way to describe features, like by just sticking a vector, like, these, let me turn on my pointer so you can see what I'm talking about. So like these things, they're it's basically like an embedding, a vector per node. And that can describe the node itself. But and that's basically sort of what you'd have in a traditional data set. You'd have like a row for like every sort of item that you care about, and you can have some way of describing that basically. But the additional, the rich and complex part is basically what nodes connect to what, and that's described by these edges, and that's what forms a graph. And so it's a really nice way to express relational complex information. And it can get really, really interesting because you can have you can describe edges with embeddings as well, and really it's a compact way of expressing a lot of information. And so that's what we want to do. We want to take advantage of this extremely nice representation, but the current, previously we had neural networks that couldn't really operate on graphs. They required images for convolutional neural networks, or like tokens, and generally just vectors of some kind is what we use. However, if we can take advantage of this, we can really do interesting things. Some of the applications we're going to look at today is zero-shot learning, and applications in reinforcement learning. So zero-shot learning is learning with basically no training examples. So in the current classical paradigm of machine learning, we have some amount of training data. We train on that, and then we are evaluated on a class. Right? So it's like, you have to learn to classify dogs and cats. You see examples of dogs and cats. What this thing does, what a graph lets you do, is that if you have information in this nice, complicated way, you can learn to identify things that you've never seen before, but that are similar to things that you've seen before. And we'll get into that in more detail later on. And it's a very recent paper, 2019, I think, that's very, very impressive in terms of the results. And actually, we have some people at Brown who are doing some of the state-of-the-art work on this. Stephen Bach's group is working on these things, I think. And aside from that, we also have, graphs can represent common information. So we'll see more of this later on as well. But the idea is that you can express a lot of things in graphs, right? So we want to be able to take advantage of these things. It's really helpful for the tasks that we want to do. And so what is sort of the base idea of how does one take advantage of these things? The idea being that, how we said we have a vector per node, right? We have a thing that describes each node in the graph. So we call this the embedding vector for each node. The idea is you want your node to basically combine information from its surrounding embedding, like its neighbors' embedding vectors and its own embedding vector. And most of graphical networks can be split apart into basically two steps, which is called the aggregation step, which is what I just described, also called message passing. But the idea is that you take the embedding of yourself, so your self node, and the embeddings of your neighbors, and you can combine them in some way. You can take the average of them, you can take the sum, the max, so on and so forth. And this sort of propagates information, through the graph. And the update step describes how to update that node. So given that you've combined your representation with your neighbors, how do you change your representation to incorporate that information? And a classical way to do that is, you have some weights if you want to sort of learn how to modulate the amount of information that your neighbors provide. And then you can have a nonlinearity to like sort of, incorporate, like, and basically you can have multiple layers of these steps, and that increases how much information, like how far you look for, because you can have your neighbors information come in, and you want this nonlinearity, so this each layer learns different things. Sort of in the same idea as why we use nonlinearities and multiple layers in classical neural networks as well. What you can also do is instead of just operating on these nodes, right? So one way of thinking about this is that the important things you care about are the nodes. Like imagine the nodes are people, and the useful bits are the nodes, and the things that you want to eventually do things on are the nodes. The graph is just a way of representing information about these nodes. And for that, we want this kind of setup. So what we have out at the out of it is we have a very rich embedding per person, for example, that represents not only the information about them, but also their social network, for example, like the friends that they have, the kinds of friends that they keep. Such a network can extract this information out of the graph. But you could also imagine like wanting to do things on the whole graph itself, not only just the nodes. And you can think of like trying to classify graphs themselves into like different types. That's one way we might want to use graph neural networks. And so people have come up with architectures that sort of summarize a graph almost. So you have your traditional aggregation and update steps, but you also have pooling, which basically says, all right, if I have 5 nodes in this cluster here and like 6 nodes in this cluster here, can I like make a super node that sort of combines all of these informations and reduce the sort of coarsen the graph, reduce the number of nodes in the graph at this step. And the idea of doing this is that you gradually sort of extract higher and higher level information out that captures more of the graph as you're doing it. And then you have, so this is called the pooling step, and then you have a readout step, which eventually summarizes this coarsened graph. And a lot of ways people do it is they just sum up the nodes of the embeddings for each node, and that gives you basically a way of describing a graph. And then you can use this graph to classify that graph. You can use it in a component for like an input into a different component of like a larger system, for example. I think I'm going to stop here and also ask you guys to please ask me any questions you have. Feel free to interrupt me. Tell me if I'm going too fast. Tell me if you'd like me to go back a slide, anything like that. And I'm going to check questions here. Anyone have any sort of confusion, things I can go over again before we really dive into the meat of things? All right, okay. Guess we'll keep going on then. So now that we've sort of gotten the base idea, right? The idea is that we want to combine information from different, our neighbors and ourselves. Well, we can look at some techniques on how to do this. So one of the things that came out, not super recently, but not that old as well, is message passing neural networks. And this can be seen as sort of a generalized structure for most GNNs. This is when the authors came up with this, they were seeking to describe and like sort of provide like a general form for GNNs, and like they abstracted all the little bits out. And this is nice because this lets us sort of understand what's going on and identify the math behind those two little pieces that we talked about, of aggregation and updating. And when we get to GCNs, we can see that this is going to be actually a special case of these message passing networks. And I'll show you how that special case comes about, basically. So what we can basically what this consists of is you can think of a message passing network as sort of k layers stacked on top of each other, and each layer is composed of three parts. Each layer is composed of two parts, and then there's one extra part at the end. So we have the update function and the aggregation function, as we talked about. And the way this works is this like piece of math describes how like each embedding, so H represents the embedding of some node V in the graph. For example, you can think of this red node here. That's the the V node that we're talking about, and the 7 is its embedding, for example. And these are the embeddings of all the other nodes in the graph. What we'd like to know is we'd like to say that, okay, given your embedding, your previous embedding, so the one that you had just as you started this layer, that plus the embed that combined with the embedding of your neighbors. So the n of v is the neighbors of v. So in this case, it would be 1, 4, and 5. So and they all have their own embeddings, right? And that combined with basically this represents like a vector representing the edge. We don't do this in this particular graph, and most people tend not to do that. But it's always an option that you could, because it's an extra piece of information in the graph. So for example, if you wanted to highlight that this 5 is a different kind of relation than the 1 and the 4, then that's where you'd put that information in. In like a more concrete sense, it's like if this person has 2 friends but has a parent in like a social network, then you'd want to identify the parent as different from friends, and so that would be captured in by this like edge relation over here. That's lets the network sort of, it gives it more information, and it lets it treat these two different pieces separately. But yeah, given this information, given 1, 4, 5, and 7, how do we update? How do we combine this information? And over here, all I've done is I've decided to just add them all up, and I've ignored the 7 in the middle, right? So the inner bracket here is like one example of this aggregation function. I just sum it all up. And then what we have is we have this sort of u of k, which is the update function. This describes how you would update your representation. How does the 7 change given 1, 4, and 5? And like a way of doing this is, I just simply multiplied the embeddings together and then put a non-linearity after it. And so this would be like, it'd be like 7 times 10, 70. It'll be 70 basically. And then we'd replace the 7 with a 70, and then we'd go on and then do this for all the other nodes in the graph. And that's how a message passing network works. The idea being that, these nodes are passing messages to each other along their edges. The 7 is getting information from 1, 4, and 5, and they're basically it's getting messages across from these different nodes. And then we have this readout function, which is at the end of our as you can see, it doesn't depend on k. At the end of our thing, what we can do is we can summarize all the nodes. So one way to do this, we just add up all the things once we're done. And then we have like a number that represents this graph. And then we can go on and do things with this number, as we talked about before. So I'm going to stop here again and ask questions because I've gone over a little bit. And this might be confusing, but please stop me if there are any questions. Okay. I want to briefly mention a little bit of how people have improved upon this. So I think this was 2017. The sort of improvements that have come after this in the context of message passing networks basically modify this update rule to solve some incremental problems. So for example, some of them have better memory for large graphs. A potential problem that some authors have identified is that when you do this step, and you can sort of intuitively imagine, right? You could imagine different configurations resulting in the same sort of embeddings later on. And then when you do your readout and you summarize all the information in, you get a vector, but that doesn't have to be unique. You could imagine different graphs resulting in the same vector if you pass it through the same network. And that's sort of called like a hindsight problem, where you can't tell what you started with. You can't distinguish two different things because they've passed through the thing and they have the same sort of output embedding. And so people have come up with modifications on how to sort of change this update rule to allow for that distinguishability in like a mathematical sense as well. And that improves performance. In some cases, it doesn't matter a lot. In other cases, people have come up with using attention. So if people are familiar with attention in the context of natural language processing, they use that in this update rule as well to sort of modulate how much each of this matters. All of these information, these nodes that exist in the world. And that's one, it's like a soft way of combining information in this aggregation function. But it still very much fits this sort of, generalized paradigm. Yeah, and a more specific way of sort of doing this is we can sort of identify, like, a more realistic example for these M and U functions, right? And that's that's how you get to a GCN. A GCN can be viewed as like sort of a special case for both of these things. And what that means is basically we say our aggregation function, multiplies a matrix. It's like a symmetric matrix this is not that, but it multiplies a symmetric matrix with your embedding. And that embedding basically captures, and you do this for all of the nodes in the graph, and then you add them up. So this captures information across all of the nodes, like we talked about. And what you can do is then once you've aggregated this, you have your update step. Now, instead of just sort of assigning it or sticking on nonlinearity over it, has this learnable filter, which is how we get our convolution going on, right? People sort of define graph convolution as looking at taking the embeddings of all your neighbors, combining them in like a way that's defined, and then combining that and multiplying that with like the parameters of your filter, and that gets you sort of your output, and that's how you do convolution in this graph case. And then you have your nonlinearity, of course. And it's sort of it's symmetric because there's a little bit of subtlety about how you define this a bar. It's based on the adjacency matrix, which is what I have over here of this graph. But the idea being is that C will also incorporate, it's the same graph from before. So C will incorporate information from B, D, and E. And so we have this adjacency matrix over here. And based on, how many nodes this is connected to, so we have degree 3, that's what our, D matrix stands for. And you can sort of see how this would now become convolution, because you have these learnable filters that you can stack and treat this basically as convolution. And one way of also thinking about this is that this is sort of generalizing image convolution, because what is an image but like each pixel is connected to its neighbors, and has like a value, like an embedding of the RGB parameters that it has. And so graphs, GCNs, are sort of a generalization of traditional CNNs. And ways people have sort of improved this is they've experimented with different ways of defining this a bar that incorporates different information and has different properties, and different ways of sort of combining these informations across your nodes. And we use, I think in our research, we've used mean sort of for just empirical reasons, but there are like theoretical concerns that people try to figure out when they're using these different common aggregation functions, essentially. Stop here for questions if there are any. People are sort of wondering about things. Okay. All right. So yes,
actually,
please,
I see you have a question in the chat.
Oh, okay. I do not have the chat open. I would love. I should keep that. Okay. Biases in such networks. Great question. Okay, so when you say biases, do you mean biases in the graph, or do you mean biases in like the traditional machine learning sense? Okay, so biases in the graph. That's a good question. In fact, that's an active area of research. I'm not. There's no real good way of. It's the same as how you deal with the bias in a data set, actually. Um, which like so it depends, because one way of thinking about this is if you have a data set, like if you remove the edges between these things, what you have is you have 5 pieces of a data set. You have like a thing that identifies a node, and then like a vector that describes the node, and that's basically a data set, right? And so if some of your things are biased, like say imagine like 2 of these belong to one class and these 3 belong to a different class or something like that, and then you have these class imbalances, and so that's like a way of representing bias. This graph stuff sort of just adds more complexity to that. It's just like now you have a different dimension of the bias, where like you could have certain relations being more prominent than others based on the characteristics of the node, for example. And there's no real good way of dealing with bias in that sense. um, so yeah, it's a hard question. It's an open question. I'm not really sure too many people have thought about that, but I could be wrong. I haven't done literature review of that sort of field. Um, it is interesting because it is very important, given that it's a great segue. So given that some of the sort of data sets people tend to use when it comes to graphs are social networks, so like Reddit, and Reddit is open source, or not open source, but they have an open source data set, I think, but they don't like Facebook, also example of a graph based data set. And these things, because they're very social, tend to be about a lot of people, and so are very likely to have biases that are very like glaringly obvious to society, I think. um, and it's more important it's sort of more, not necessarily more important, but it's more obvious and more prominent in these sort of data sets. um, so it is a very important question that we should all think about in our research. So that's a great question. um, and as that segue, so what kinds of information, I said that we have a lot of complicated information that we can represent. What are some examples of what people have done? um, So some of the things that people have done is citation networks. So when you do research, understanding who's citing who, and what people are working on what kinds of projects. So one way of thinking about it is a paper is a node. Paper has authors, or authors are nodes, and authors write papers, um, and different authors write papers with different other authors, and they cite different other authors, and so you have these 2 different edges, and that creates a graph, and then you can do things on this graph. And so that's what this basically is. And you can classify different papers, I think, and so on and so forth. And people, publish results on these things. An interesting thing that I didn't really know about until I was preparing for this talk is you can think of a chemical molecule as a graph. Um, so you have atoms, and they're connected to different atoms, and then the way they're connected is sort of your edge type. And that lets you sort of, and this, graph neural networks is a great way of sort of performing machine learning on biochemical things. And it's showing good promise in the last couple of years as a way of sort of dealing with that information. Interesting to all of you physics people, maybe. And then, of course, we have your prototypical social network. People have information about them, and then they're connected to different kinds of people in different ways. And so that's that very, prototypical sort of graph. And then you have a bunch of other stuff. Nell has gotten really popular lately. And it's a very it's got Nell and Neil is, I think, a subset, and it's a very prototypical graph sort of thing. 2 important things that are not mentioned in the traditional graph literature, but that are kind of in use in a lot of different places is is one. So ImageNet. If you guys aren't familiar with ImageNet is this 1 million data set. It's basically a big data set of images that has a bunch of classes, and the goal of the ImageNet challenge is to identify and classify images based on all the things that are there. It's your classical supervised learning problem, and people use it a lot in computer vision. It's sort of the traditional standardized benchmark. What you can do is you have this WordNet sort of compilation, it's a knowledge base that orders like nouns based on hierarchy, and most of these ImageNet classes are in WordNet. And so what you can do is you can extract hierarchy. So you have gorilla, snow leopard, lion, and Ihasa. And you can classify all of these into a big like sort of tree-like graph with all of these things, having like parents and so on and so forth. And so you have a graph representing ImageNet. And as you'll see later, this is what people use for crazy zero-shot learning achievements and things. And another sort of similar but not quite is less tree-like is ConceptNet, which represents just like generalized common sense knowledge about the world. So like that like an axe is a tool, right? So that kind of information will be present in this knowledge base. It's semantic. It's a knowledge graph. It has common sense knowledge, and it's extracted from language, and it's tied to these. It's multilingual. It has support for some quite a few languages, and this describes how it's made, what it's made, and what it has. But basically, the idea is that you have like nodes that represent different things, and they're connected with very different relationships, like ISA, so on and so forth. And they have like synonym relationships, and it's a very, very rich source of universal sort of common sense knowledge about the world that you can take advantage of in really nicely in reinforcement learning. And we'll see a few examples of that later on. So yeah, jumping into zero-shot learning. What, as I talked about before, we have this sort of hierarchy of ImageNet classes, and we have basically a knowledge graph of them, and we can use that to learn things in a much nicer way. And what you can think of is, if your knowledge graph has, for example, 3 classes, it has deer, zebra, and this okapi thing. The idea being that, the description of an okapi is like a zebra-striped 4-legged animal with a brown torso and a deer-like face. From that description, you can infer that, it's likely, it's connected, as a person designing this graph, you should connect it with zebra and deer because it looks kind of like zebras and deers. So if you have this connection over in your knowledge graph, what you can do is you can sort of train a graphing network to take in like this graph and embeddings describing this sort of each class. Like zebra has like a vector, deer has a vector, okapi has a vector, so on and so forth. And you can generate classifiers. So this is kind of like meta learning in some sense, where you have a network spitting out something that will classify things. And that's how they do zero-shot learning. The idea being that if you have a way of embedding a word, you can embed a copy, stick it into your graph network, and then it will spit out a classifier that is somewhere in between the classifier for deer and zebra, for example, because that's a copy is a thing that is connected with these. So the classifier that should do well on a copy should do well, like it's sort of similar to the ones that would do well on deer and zebra. And this, based on the fact that you have an embedding for the words and they're semantic, and they're connected in the graph, for example. So yeah, it's achieved really cool results. It does way better than chance. It basically it can run inference on like thousands of new classes that it's never seen training data for before, and still do pretty good. Not great, but like 1 to 2%, which is far better than most of the previous methods that have not used sort of graphs. And another sort of use case that I want to talk about is some of my own stuff in reinforcement learning. And I'm not sure if people are super familiar with it, so I put a reinforcement learning crash course for y'all, so I can sort of give the lowdown on reinforcement learning. The idea in reinforcement learning is you have 2 things. You have the agent yourself, who acts in the world, and you have the world because you need somewhere to act in. So we call it the agent in the environment. The agent has a bunch of things it can do. For example, like imagine a robot. You can move forward, you can pick something up, you can throw something. You have a bunch of things you can do. Really, it boils down to like moving your arms, right? So those are the actions that you have. And when you do these actions, the environment changes in some way. So concretely, what we have is that we have like a world that says, okay, given that this action has occurred in the world, the state of the world must change some way. For example, if you throw like a glass piece on the floor, it's probably going to shatter. So its shattering is a change of the state of the world. And so what this does is this sort of changes based on like this thing called the transition function, which describes how things change. And then we have our state S moving to state S prime given that action A. And this describes how things change, but it doesn't describe what the agent should be doing. And that's given by this reward function, which says, this is how we tell the agent what is good and what is bad. So we say, okay, Matt, like, do this thing that like gives you the highest expected discounted reward. So from now, take the action that you think will give you the most reward in the future, on average, given that future reward is more uncertain than current reward. So take that into account. And this is sort of like a general framework that lets us create good robots that learn and do things in the world that we want them to do. And a bunch of subtlety here, but for now, this is sort of a very high level overview of what is reinforcement learning. And what I really want to focus on is how we stick prior knowledge into reinforcement learning. So, for example, like we remember this sort of concept in hierarchy stuff, right? So if you know that like tools are like an axe is a tool, but so is a pickaxe. Like a pickaxe is also a tool. They're all tools. This should let you sort of think about things in interesting ways, because it's like, okay, if I have learned that in this world, a pickaxe behaves a certain way, an axe behaves a certain way, I can infer that any tool behaves that certain way, right? So just common sense knowledge about the world that humans take for granted has a lot of promise and applicability in reinforcement learning. And so in the last few years, a lot of authors have tried to inject this and use it to improve reinforcement learning, often to great benefit. So one thing that we're sort of considering is package DQN or prior knowledge graph DQN. Used to be called graph DQN. I don't know why they changed it. But what this does is basically it incorporates prior knowledge for reinforcement learning in a very specific way. So it's sort of your just like prototypical, I take a GCN, I take reinforcement learning, I smash them together. This is, I think, the first paper that came out with this. So it did the very, simple thing and like, oh, look, it works, which is great. Because if it didn't, we wouldn't know what to do. So things to note are that, it works on a symbolic state. So it can't look at an image, but it needs like a way of telling it that it's, like basically it works on this, not this. Which means you can't just point a camera and then have like your prior knowledge come into play like a human would. And then it has a bunch of sort of graph convolutions, like the same ones we talked about before. You have your knowledge graph. Each of these, the edges have like embeddings. The nodes themselves have embeddings, and you have this sort of, complicated architecture that does all these things. And eventually, you have like a reinforcement learning agent at the end of it. This sort of incorporates some of the pooling architecture stuff we talked about and this readout thing over here, which is interesting because it's not just aggregation and updates, but it's also this pooling thing because it wants to modify the graph itself and coarsen it and sort of densen it and change those attributes of the knowledge graph as well, which is an interesting way to do it. It's but a consequence of that is it's very like sort of, it's a very heavy architecture. It's not really modular. It's, if you change a bit of pieces here and there, it doesn't work quite as well. But this was sort of the first thing that tried to use knowledge graphs in reinforcement learning and to great success. Another sort of work that came up more recently is scene priors. So the idea in this setting is not like a generalized, oh, do whatever you want, arbitrary world, arbitrary agent, you have a reward function. But the idea here is that, in a realistic environment, say in like a house, right? You're in a house, there are a bunch of rooms. You have a camera that looks at all these realistic things. The goal is to find a thing. So I will tell you a robot what to find. I want it to find me a banana. And so its goal is to look around and find me a banana. And when it learns all these things, at the end of it, I should be able to say find something that it knows about, and it should be able to go find it quickly. Um, and how it works is that it says, okay, in the camera, I'm going to identify all the objects in the scene using like an object detector. I'm going to see, all right, what are all these things? I'm going to see what I'm supposed to be getting. So, for example, in this image, it's supposed to be finding the television. It sees certain things. So it sees like a couch, or it sees like a TV remote. And you can see that in the graph, TV remotes tend to be in occurrence with television. So when you have a TV, you have a remote generally. And so if it parses that using its graph convolutional network, the thing that we saw before, and given that it sees this, it knows that if it sees a remote, it should find a television. It knows that it's finding a television, and it can see a remote from its actual camera. If you combine all these things, you could sort of imagine that the right thing to do is to go towards the remote because you're likely to see the thing that you're supposed to be finding. So that's sort of the intuition behind how this works and why it ends up working. It works pretty well. Some more details about the graph are like, you have like a mug. A mug is on a table. It is in a cabinet. So it has all these very specific edge features that it ends up using in this sort of convolutional network. And they have it over here about how this works. It's similar to what we said. We have like an embedding for each node. We do your sort of A times the previous stuff times your weights, or your convolutional filter with your nonlinearity, and then you do that a bunch of times. And then sort of their readout function is they concatenate everything into a big vector. And so we see the same sort of principles come into play again and again of aggregation, updates, pooling, and readout. And those are like really the building blocks of graphical neural networks in general. And sort of the next sort of piece that I want to talk about is my work. This is a poster that's going to appear at NeurIPS later this year at a workshop. And I'll break this down into pieces a little bit. But the idea was that we compare to these guys, so GraphDQN. And what we've identified is that in a very specific reinforcement learning task called multitask reinforcement learning, these guys, they don't really do as well as we'd hoped. And so we wanted to fix that, and we modified the architecture and introduced some new things along with a new domain that lets us do way better on multitask reinforcement learning. So with multitask reinforcement learning, the idea is that all of this stuff stays the same. So the environment and the transition functions stay the same. The agent has the same actions. There's the same set of states, but the reward function changes. So the thing that you're supposed to be doing changes. And the idea is that you should be able to use the things that you've learned in other tasks to do better. It's similar to this sort of thing where like the thing that you're trying to find changes, but the place you're finding things is the same. But this is hyper specific to finding things, and we didn't want that. We wanted a little bit more general things. And so how the best way to describe this is sort of we come up with this new environment called Symbolic Production that is a simulator that says, okay, the idea, it's sort of inspired from Minecraft. If you guys are familiar with Minecraft, the idea being you have a bunch of different tools. So in Minecraft, you have like a pickaxe, you have an axe, you have a shovel, you have a sword, and these tools are meant for different kinds of blocks, right? So a pickaxe is meant for like stone, but a shovel is meant for like dirt, and an axe is meant for like wood. So each tool has associations with different blocks, and you can capture that in a graph. So for example, you can imagine this being axe, and this being like birchwood, and this being oakwood. And birchwood, if you chop down birchwood, it gives you like a little birchwood cube, for example, in Minecraft, right? And then you could imagine this being sort of stone or pickaxe, and this being stone, and this being like iron. And when you do that, it gives you like little blocks of those things. But you can't really use like an axe to chop, this, and you shouldn't really use a pickaxe to chop wood. That's not how you should be doing these things. And so this basically is an abstraction over that. It lets you spawn this out to like hundreds of different tools, and it'll randomly configure them for you. And our domain looks sort of like this. It's a symbolic domain, similar to the DQN, so we could compare them. And what we do is the goal is you're the agent. this is a little bit hard to parse, but the goal is that what you do is, you know that if you need to get number eight is this thing. So you should use block tool 2 on block 4. And so now you need to go pick up 2. So you go here and you pick up 2. And then you go all the way here, which is what this thing does. So now you're here. And now you can use 2 on 4, and then you get 8 over here. And it drops 8, you go and collect it, and you're done. That's sort of the objective of this domain. And our sort of architecture looks sort of like this. What we have is we have a thing called an object embedding, which is a vector for each sort of object in the world. So you have a vector for 2, a vector for 3, and so on, like 4, 5, 6, 7, all the way to 11. And given these vectors, what we do is we like stick them onto this and pass them through a graph convolutional network. And then this, I'll go into more detail about that in a second. And then we update these object embeddings. So these are like sort of nodes in our graph. We update them, and we don't have a readout function because we don't, or pooling because we don't want to keep, keep things simple, and we want to use just the embeddings themselves. And then we basically say, okay, now that you know that like a 4 is here, take what a 4 is, stick it in there, and do reinforcement learning on it. And the idea being that you can incorporate this sort of knowledge about the world that you have in this graph to do really well. And this graph sort of stays the same across whatever the goal is, right? It's all talking about the same set of things. So in theory, like this with the proper design of our architecture should let you do much better. And what is that design of architecture? It's basically this. So we have our initial embeddings, we have our graph, and we do our sort of our A hat transpose the previous things times some new weights that we talked about plus a nonlinearity. We do some things differently. We take the average of the embeddings when we're doing that, because we found empirically that summing tends to explode the values of the embeddings, but average has also problems. But in practice, we find that it's a minor difference between everything, and there are ways to deal with them. But these are all like sort of empirical details that don't matter that much. And this is how our graphical network works basically. And what we have is we have really nice results. So for example, our graph is the one that actually goes all the way up. And so this on this axis is a reward, and this axis is time steps. So how long it takes in terms of like environment steps. So each time you take an action, we have a tick. And based on that action, what reward did you get? So that's sort of what this graph represents. The thing that's basically flatlining is the previous work that the previous state of the art. So these guys, in like multiple tasks, when you switch out the reward function, these guys can't do super well, and so they tend to falter. And our modification is we don't do the pooling and readout functions that they do. Because we find that it really conflicts with the multiple task setup, and so we get pretty good efficiency and learn pretty quickly, even in very large domains. So like 64 by 128, it's like a lot of tools with a lot of edges in the graph, basically. And so for future work, what we want to do is move this to like a rich like pixel-based domain, and we want to combine multiple sources of knowledge for different kinds of reinforcement learning algorithms. Thank you. Please, any questions, feel free to ask. I know I've managed to just hit time, but.
Well, so then I guess if no one has any questions, I'd just like to thank you for giving this talk. I think this was really nice and very informative. So thank you a whole lot.
Thank you, Bern. Thank you, everyone, for this opportunity. It was a great time. Get to,
Oh, it looks like you just got a question in the chat.
Oh, perfect. Let me pull that back up. Sure. Let me do that real quick. So let me go back to the zero-shot learning slide. So it's relation to unsupervised learning. Interesting. I wouldn't say this is unsupervised. I think you could sort of move this to unsupervised learning. So unsupervised learning, for those who are not super familiar, is when you don't have any training data at all. right? And so and not you don't have any training data. I'm sorry, that's zero-shot learning. But when you don't have labels, so you can imagine having a bunch of images. So you have all these, deer, zebra, okapi, but you don't know what each of these are. There are no labels. You just have images. And what unsupervised learning tries to do is it tries to get sort of a representation generally. It says, if I train on all of these, images, can I get a way of, describing an image that's very useful and captures information about what's in the image? And then what I can do is I can use that and fine tune on a very small set of labeled examples, because labeled data is expensive and difficult to come by. And ideally, what you can do is if you have a general way of understanding what an image is, you need less data to do really well on actually classifying when you have labels involved. It sort of separates understanding what is a thing versus understanding what things are there into two different sets of processes, and tries to do well on both. And in this, it's sort of different because we have labels for some things. We have labels for the things we know about. So we know about zebra and we know about deer. So we have labels and data for both of these things. And the idea is that we want to, it's sort of the flip direction where we have no data, but we have a label. So we have okapi as a label, but we have no examples of what an okapi is. And we want to still do well in that setting. So it's kind of like not the opposite of unsupervised learning in some sense. But yeah, I think that's what the relation between